So welcome everyone out there. We welcome questions in the chat, and the three of us are talking today about sustainable and explainable AI. And I'm John Crowcroft. I work in the computer lab in Cambridge and at the Alan Turing Institute in London, where I have the title of researcher at large, because it's like Paddington at large, somebody who walks around causing serendipitous accidents. That's how I view my job there. And with me, we have Adrian Weller, who is also in the University of Cambridge and also in the Turing and looks after AI and all kinds of interesting things. And Neil Madhavapeddy, who's also from the computer lab, but not from the Alan Turing Institute, as far as I know, and looks after many cool things in the systems area, but more recently in carbon credit, and has got some very interesting work in environmental side of things. So we hopefully, and has previously worked in very large-scale cloud compute deployments, which is relevant here in terms of the sustainability. So I'm going to talk for about 10 minutes, and then I'm going to ask each of the other two some questions that I have pre-cooked for them. Some of the things I say are intentionally contentious, and that's, so maybe they'll respond to, maybe Adrian and Neil will respond to those being contentious, or maybe they'll agree, and then we'll agree that there are bigger problems in the world than I allude to. So basically, this is being beamed to you under the auspices of IKVA, which is a Cambridge startup that does AI-based stuff. But the three of us are doing this out of our academic research world, which interacts with industry as well as students and research. So that's kind of our sort of mix of background very briefly. So I'm making a few jokes along the way, so feel free to chat and put the laughs in the chat. They're not very good jokes. I'm bad at stand-up comedy, which is why I'm still an academic. But there's this very famous thing about AI is basically things we don't understand. And an awful lot of AI comes out of traditionally a long time ago out of statistics, which are hard to understand, and many people make many jokes about statistics. But in between AI and statistics is this thing which we kind of understand and automate statistics, which is machine learning. In fact, you can often see systems that are all three of these things, and we can allude to some of those. But what we're interested in this talk is two aspects of systems that implement automating statistics, whether it's machine learning or AI. And one aspect is the explainability, which is quite a subtle business, and there's many different lenses you can look at explainability through. And the other is the sustainability, and that the two aspects to that there is how sustainable is your machine learning system, your algorithm and your implementation and the platform you run it on, but also in both of the areas of explainability and sustainability, there's the application of AI to the problems of sustainability and explainability. So it turns out, for example, many of the almost cliche or at least stereotype problems for explainable AI often turn out to be biases in input data. And then it turns out that the humans were acting on that biased data or making biased decisions, which is why your data is biased. And actually, in the process of figuring out that your AI is in the process of explaining why the AI is making biased decisions, you actually fix a problem with people. So that's kind of one of the directions where you go with explainable AI. It can go both ways. It may help improve our understanding of what people are doing, and then actually debias their behaviors, which could be good. And similarly in sustainability, we could look at the problem of sustainable computing in general, which is a big topic. It's been going probably 20 years now since I think Andy Hopper in the computer lab a long time ago was one of the first people to observe this was an issue. And sustainable computing and AI has just pushed that to, in some cases, unsustainable extremes. But also the use of AI to understand the planet and the ecosystem is definitely an interesting application. And it may be something where we can make a virtuous cycle there, which will be good. So if you think about simple statistics, it goes back to the origin of, but way before computing. We would have actuarial tables, or we'd have ordnance tables. And the two of the main uses of tables were for firing missiles at people, or computing when and whether they were likely to die, so you could work out what the insurance rate should be for them, or how many ships would sink on so many journeys, and so on. So that's a lot of the origin of statistics, where people would compute books. In fact, I noticed in the Castle pub recently in Cambridge that there was a 19th century book of tables of statistics lying in the corner of the pub. I was thinking, what on earth was it doing there? Somebody obviously left it there as a souvenir and decided it was no use in their degree anymore, and it must have been there for nearly a century. Statistics move through into technologies like communications, where things like maximum likelihood estimation are used to figure out what your optimal coding and modulation and coding techniques were for communication, going back to Bell Labs 50, 60, 70 years ago, I think. And as we go down this list, we get to more and more complex systems, but not necessarily not explainable from a statistical basis. So classic things like linear regression and other forms of regression, often used to figure out what's correlated with what, which is useful for figuring out what you might do about things potentially. Random forests are used often to figure out what kinds of decision support you might make. And then we move on to kind of where deep learning came in, and artificial neural nets, which have been around for a very long time, but relatively recently took off as being incredibly successful at certain classes of machine learning, originally, I think, for recognizing or classifying images. I wouldn't say recognizing, because that implies they're actually intelligent, but certainly that's sort of one of the classic applications. And various more complex uses of neural nets, or ways of building them. GANs is sort of one technique used by DeepMind very successfully in several areas to build systems that are really good at doing what they do. And as I mentioned, as we go down this list, we get to things that are more difficult to understand why they do what they do, why they support a decision A rather than B, or they classify images as having this feature or not having this feature, when it may be there are multiple dimensions, very large numbers of dimensions to that. And as we get near the bottom, we're going to go on to a couple of more things. I think one is an extreme case of something which is really hard to understand, but is incredibly successful, which is these large language models or foundational models, which you've probably seen around the world very recently. People are raving about these fantastic images that can be generated with very simple text input that look like beautiful science fiction movie scenes or magazine covers or whatever, but also text. The OpenAI GPT-3 chatbot seems to be quite a big thing in the last few days. These seem to be quite effective again and convincing people that maybe they're quite clever, but why are they doing what they do is not obvious. And the last thing I'll mention is sort of Bayesian models, where we actually have fantastically good understanding for, again, 150 years maybe since Sir Reverend Bayes came up with the model. And there are tools that build on these systems. The last four things on that list, though, are typically, or 3 out of 4 of them tend to be black box. Bayes is not a black box. It's something we can get what the output system is, but they can be quite expensive computationally, and particularly foundation models, or large language models, which have 300-400 billion parameters. This is difficult to see how it can be made cheaper. So that's kind of where we're heading with this whole area. So effectively, there's a collection of different techniques for thinking about explainability, and I'm going to revert to Adrian in a bit, because he's certainly far more expert in this area than I am. But when we have something that's classical statistics, we have written down some equations that describe what we're doing, and you can see what we're doing. It's like visible, it's self-explanatory, if you like. But when we have black box AIs, traditionally black box AIs like a neural net, at least until relatively recently, these were very hard to figure out what they were doing. Now, there are several different ways there's several lenses you can look at a black box AI through, and one of the techniques used to understand what it's doing is to feed it counterfactual queries and then see what the output is. You say, is it because X, you vary something about the input and see how it changes. And you can do that in more than one dimension. And that's one technique. You can also examine the relationship between all the features in the inputs and see which ones are important, using like Shapley values, for example, is one technique for that. There are lots of others. Graph neural nets, there's a technique called attention, which actually tracks the impact of inputs through the neural net. And there are other techniques where you can actually study the statistics of the weights within the neural net as they vary through training, and then work out what are the actual features that are being extracted by different parts of the network. There are other techniques. We don't have time to go into the whole part of these, but that's it's relatively hopeful, but I'm going to say relatively expensive at the moment. But there may be interesting ways forward to deal with combining better explanations and managing the sustainability at the same time. And GANs are actually very interesting because, of course, you actually can start from some kind of model anyway, so that actually can have good explainability, although they can be quite expensive, so that in terms of computational cost. But that may also be because the problems that folks like DeepMind have tackled have been inherently very large problems. I mean, their AlphaFold work, for example, looking at protein folding, is absolutely extraordinary. The scale of the problem was always known to be extraordinarily computationally hard, and it was never going to be a simple thing to solve. So the fact they've tackled that pretty seminally recently is really exciting, and it may that's good. So in some of the large language models, they're I think what are commonly called few-shot models. It seems like there's kind of not a lot of hope in explaining, although actually maybe recently there have been some explanations of how they're working. And one of the things I've read most recently is something that said they work on ridiculous things, and things that are what some people call the clever hands thing, which was the horse that was able to do simple arithmetic, but then it turned out on close examination the horse owner would smile more when the horse was getting nearer the right answer, and the horse was just really good at recognizing human happiness. So and some of the recent looks at some of those systems have noticed that they're kind of learning off rather strange combinations of things that happen to coincide in some way with other things. So that's a problem with other approaches too sometimes. So that's kind of interesting. And then, as well as counterfactuals, of course, the other lens to look at explanation through is who you're explaining for. The classic thing in a medical diagnosis system, for example, is you have at least two customers for explanation. One is the doctor, who a human in the loop, who may be an expert and may have their own diagnosis. You want to say, why does the AI say diagnosis X? And then the other is a patient. And there are other examples of explaining what somebody's insurance premium will be based on the inputs. They're two different people. There's the insurance company that wants to know why is it not making as much money this year, and then there's the other is the individual getting told the premium has gone up or down this year. And so the complexity of the explanation varies there as well, and how you arrive at the explanation. The counterfactual may be good enough for some people, but if you are trying to diagnose what went wrong with your AI that drove a car off a cliff, you may need to have something that explains what it was inside the neural net that misrecognized the police telephone box for a TARDIS. Sorry, that was a joke. Okay, so yeah, sustainability. Turns out there's a lot of work in making some of the more complex AIs more sustainable, and it goes back quite a long way. And actually, some of it coincides with also making systems more privacy preserving. So again, recently there's been work on applying homomorphic encryption during training of a neural net and during running of a neural net, so that you can't examine what's actually going on. You just get the output. But in the process of doing that, people have reduced the size of the neural net by compression and reduced the complexity of homomorphic operations by replacing floats and reals with integers or even binary weights in the neural net. And that, of course, increases the efficiency, but adding homomorphic encryption makes it massively more expensive again. But if you throw away the privacy requirement, or you do the privacy a different way, you can get big improvements. And compressing neural nets, even lossily compressing a neural net in the same way you lossily compress an image, throwing away edges and weights that appear to be not very important, is the sort of thing you would do when you've trained up a neural net and you want it to recognize faces of specific people in somebody's camera, and the camera doesn't have a lot of compute memory resources to run the thing. And that appears to be very successful. That suggests there's a sort of way forward. It also suggests that the apparent complexity of things like deep learning is possibly illusory in many of those sorts of examples. It could be that the components of the net, the layers and the weights between layers and within and the feedback processes may actually, there may be subcomponents. You can put out modules you can put out that are responsible for certain features, for example, in that world. And that says, well, okay, that's actually what that's done is statistically arrive at something that was a bit like when smart programmers used to build image processing systems by knowing about the kind of features they're looking at and what the topological characteristics of those features were in classical image processing. And you can actually race the smart programmer who knows about those sort of feature extraction systems against a neural net in terms of, programming something up and see where they arrive, and then compare these. So you can actually compare the algorithm and then say, well, actually, we can do directed optimization potentially, or you could discard the neural net and just use the classical feature extraction, or you could run a third system on both that actually figure out how they combine. So there are lots and lots of ways forward. So this is the general gist of where I wanted to go. And at some level, when I've looked at one example of explainability and sustainability, and this is where we can get into disagreement. I'm going to ask Adrian to talk about this in 1 second. But this example was a colleague of ours in the chemistry department does energy landscapes, and originally he worked on the energy landscapes of molecules, and he was super interested in that. And then he realized that in the process of recognizing complex molecules, he could use neural nets to do this. Then he realized that the neural net was much simpler than some of the molecules. So why not compute the energy landscape of the neural net as you iterated through training? And every time there was a significant change in, let's say, the entropy of the neural net, you would output the input features that were important and build a random forest. And you get to the end and you have a random forest, you can throw away the neural net. This is kind of quite interesting. The problem is the cost of training your neural net now includes computing the entire entropy of the neural net at every step of iteration, which if you're doing that over lots of complex input with a lot of dimensions, multiplies or exponentiates the cost of running the thing. And it's one of the things where scientists have access to, as with people inside Google DeepMind and Meta and companies like that have access to 100,000 GPUs for a year at a time. They sometimes do things that work really, really well, but they're not really sustainable. They're not the kind of thing you could say, everyone in their home's going to run this to optimize their home energy use or something. That's not going to be a very valid way of doing things. So that's my sort of example of, well, you could say, show me your working. You say to the AI, show me your working, show me why you've added these, weights on these edges have been adjusted in this way. What was it, in collections of inputs that caused that? And then having done that, you might be able to make something more sustainable, but the cost of doing that might be crazy. Okay, so that's a very brief tour through a collection of things. And we have one question in the chat already from Ian, actually, which we can get to. In fact, maybe we could start with that question. Adrian, do you want to start with that question? We could just go straight for that one.
So first, thanks a lot for your comments, John. Those were really, really good and really interesting. If it's okay, can I start by responding to a few of the things you said? And then,
of course.
Brilliant. John's got an amazing overview of really huge parts of the field, and that was really, really helpful. But I want to maybe just press on a few things he said. And this is going to rewind a little bit because I was jotting down some notes as we went along. So I'll try and explain the bits I'm talking about, and then mention what I'm saying. So one point is about how our AI models today, a big issue with our models today is that they can be biased. That is, often what happens is that they're trained on past data. Often that past data is based on past human decisions, and we humans, it turns out, are often biased. And that's a shame. Many of us would like to try to fix that. Turns out it's not that easy to fix it, but we want to try. When we train our models on that data, actually often a helpful thing, this may some people will disagree about whether this is helpful or not, but often I'd suggest that it's helpful that once we train the model on that data, it becomes easier to see that the bias was there in the first place. So it's hard to know if people are really that biased, although you could try to do statistical tests, and you should try to do that. But often what we've seen in the last few years is people training a model on human data, they then observe that that model is biased. And then the next step is an important issue. So there was a big story about what happened with Amazon a few years ago. Amazon were trained a model for recruiting people. They trained it on past human decisions. Then they saw that their model was biased against women, which is really bad. But what they did then, I don't think was necessarily the right thing. I mean, and there'll be different reasonable opinions about this. What they actually did was they then said, OK, they threw away the model and went back to the people who were presumably the same people that were biased in the first place. What they could have done, and this is an important point, they could have adjusted their model. And it's usually a lot easier to tweak a model than to tweak humans, even if we want to try and tweak ourselves. So it's important to note, you sometimes hear sort of two phrases. You sometimes hear garbage in, garbage out for data. And along with that, you sometimes hear bias in, bias out. But in fact, bias in does not necessarily mean bias out. It's kind of a starting point. We can detect that bias, and then we can try and do something about it. And there's a whole sort of toolkit to try to do something about it. And I don't at all claim that that's perfect. And there are lots of issues about what exact bias you should be trying to get rid of. What does that mean? How you should do it? But it's a starting point. And again, often it's easier to tweak these algorithms than it is to tweak people. That's one point. The next point is about explanations in general. And John, I'm going to be a little bit less optimistic than John. So John said that there was this relatively hopeful picture because we have this increasing toolkit, and we do have an increasing bag of tools. And part of my work is trying to build that toolkit, and I think it's really important that we do that. So we have an increasing set of tools which help us look at models. Often this is looking ex post at a trained model to try to understand a bit about how it's operating. Like John said, to try to understand which input characteristics are most important to a model and coming to its decision. And there has been some good progress there. But what I would highlight is that that isn't necessarily the kind of explanations that people want or need. So if you go around and ask people, and we have some work doing this, other people do too. If you ask real users, real practitioners, what kind of explanations do they want? It's typically not the sort of thing that these models provide. Sometimes it is, and I'd say to date, most of the techniques are most useful for helping developers understand maybe where their model is good or bad, where it might go wrong, how they can improve their model. But to date, most of these methods are not so useful for people to really understand how they've been affected. And we can get into that more because there are some methods that are useful, but I think there's a lot of work to do. And a big important part of that work is not technical. It's about listening carefully to the users and practitioners and affected stakeholder groups, understand what it is that they want and try to respond and try and build to give them what they need. Another really important point is that often people think that explanations will allow us to see if a model is biased. And sometimes it can, but it's not quite what people think. So, for example, many of like we were saying, a lot of these explanation methods, they'll tell you which inputs were most relevant for making a decision. So you might think to yourself, OK, let's suppose we have an algorithm for a bank to decide whether or not to make a loan to someone. Let's just look and see whether the gender, the race was an important variable when the algorithm makes a decision. You can do that. The bad news, though, is that it turns out that it's not difficult to tweak your model. So suppose I'm a naughty person and I want to be really biased against blue people, but I don't want you to be able to recognize it. So if I just set up my model to be anti-blue people, the basic model probably will be easy for you to tell using this explanation method. But now, if I want, I can actually adjust my weights so that with very high probability, if you apply a large bag of explanation methods, it won't look like I'm using this blue variable at all, whereas in fact, all my predictions stay the same. And there's a bunch of papers on that in the last few years. So that's another really important point to take away. If you want your model to satisfy certain properties, what you want to do, it's kind of simple, is you want to verify that your model satisfies those properties. And that's not the same as looking at it with an explanation method, even though you might think it is. Maybe I'll sort of stop there with comments. What do you think?
Yeah, that's great. And I did want to, I'm going to flip between the topics slightly. So if we can go to Anil and talk about sustainability, there is a question which I think just came in, the second question, which I think you're kind of starting to head towards answering, but if we could maybe go back to that because it is important. And I think it's like, what is your a priori basis for saying that there was societal bias? Perhaps that's where, Adrian, your expertise in where we're heading with things like responsible and ethical and regulating of AI, maybe that's where we have to have humans observe humans doing the wrong thing and then, deal with the deliberately obfuscated blue biased AI somehow, some other way, perhaps. I don't know. But before we go back to that, because that is a very, very important topic, let's head for Anil and ask. My question here is, I know you've got this great project in the carbon credit world, and maybe from that or other related work, you could talk about where is AI, explainable or unexplainable work, going to be useful in dealing with making the world more sustainable?
So thanks, John. We're in an interesting time today, actually, because it's the opening of the COP15 Biodiversity Summit over in Montreal, and this is delayed by a number of years because of the pandemic and lots of political wrangling between China and Canada. But we're at a bit of a clutch point at the moment where it's not just the carbon emissions that are the biggest problem we're facing right now. So we're actually in three simultaneous crises. So we have the emissions crisis for greenhouse gases resulting in warming, but we also have more mass extinctions happening across species right now across the world than at any time in history. So I think a report last month showed that something like 69% of regularly counted terrestrial species have disappeared since 1970, and also that's just the number of counted ones, but also the number of species that we've yet to have even known existed have disappeared is enormous. And then we have desertification as well, which is the problem of drought and the lack of access to water, and that's interlinked with the problems of biodiversity and generally of climate change. So we have tons of global crises right now, and it's difficult to know where to start because these are all really highly interlinked. So one variable affecting, for example, the tropical rainforest will affect water flow and hydrology systems all the way throughout entire continents, all the way past the equatorial belt. But of course, this is where AI is a technique that does really well. Given vast amounts of data, we should be able to figure out inferences about how to start tackling problems, but also predicting how complicated interventions might have unexpected side effects, and starting to build a model of the world. So what I'm fascinated by at the moment, and what I think is a potential way to give us a way out of this mess that we've created for ourselves, is to use huge amounts of data that is available about the natural world. And so this includes, for example, anecdotal evidence gathering over centuries. For example, for biodiversity, we've had people just walking around with little collection jars and painstakingly taking notes about where they found occurrences of species, all the way up to satellite data. So we have over 10,000 satellites in the sky, give or take, plus all the spy satellites. About half of those are maybe used for Earth observations. And each of those outputs terabytes and terabytes of data across different spectral bands. And so given different resolutions, different things that we're measuring, different physical techniques of measuring them. So everything from just taking pictures to enormous LiDARs in space. There's one called JEDI on the International Space Station that is giving us more data than we've ever had before. And this has been going on for decades. So I think the first Landsat launched in about 1984. So the thesis here is that while one good use of AI is to build these smaller scale models dealing with domain specific problems, we could also try to pump in just exabytes and exabytes of data about the natural world and try to come up with one planetary intelligence that is a set of parameters trained on data that has been taken with a certain amount of bias built in from measurement bias, because there's certain techniques used to measure them. But then we have lots of different types of satellites, lots of different measurements these days, and try to head towards an objective truth about how well are we doing in terms of the hydrology of the systems, of marine health, of coastal health, and so on and so forth. And I think this is an interesting area for a lot of the topics you brought up before, because what does it mean to explain a really, really complicated physical process model? We don't really have the user interfaces right now to explain all of the weird kind of fluid maths and the higher dimensional topologies and stuff involved in these things. But a lot of our existing systems could provide natural language interfaces to explain why, for example, drilling in this particular area could be a lot more harmful than drilling in this area, or maybe the effects of doing one intervention to save a forest might result in unexpected perverse incentives somewhere else. So we've got to take in and build all these new models of planetary computing, and then try to figure out how to build in interfaces that can work in such a way that real decision making on the ground can actually use this to more rapidly take consequential decisions that will minimize harm across many, many complex different ecosystems. So I think we're still in the early days of doing that. There's lots and lots of exciting advances. But one really good paper out of Europe's this week that totally changed my thinking about how we should be approaching this was by Jeffrey Hinton. And he observes that we'll be using backpropagation for all of our training so far. And there's very little evidence that the human brain actually uses backpropagation. Like it just, there's no evidence this is actually built into our cortical systems. So, and backpropagation doesn't work very well for real-time stuff, right? Because you can't stream lots of data in and then pause for 10 minutes and then take a decision. We have to reactively and incrementally kind of build our models. So it's clear that we need a new mechanism for training these neural nets that is more in line with the physical world. And so he's proposed something called the forward-forward algorithm, which instead of backpropagation, just has two forward propagation passes and has the interesting property that can work in real time. It doesn't need knowledge of forward computing nodes the way the backpropagation does, but it's still very early days. We're not quite sure yet whether or not it works for any non-trivial problems. So it's clear that we're still working in the basic mathematics behind exactly how to train these networks. But once we crack some of these new systems, we can then do real-time incremental development of planetary scale AIs. And I think that's a huge opportunity.
There's one other thing actually, which is that going back to some of the simpler models, that we actually have physics and chemistry and oceanography and atmospheric sciences, that have models. But when you try and compute how they work, you can't easily solve them at arbitrary scale, but you can couple them using these things that the physicists call phi-ML, as in the letter phi in Greek. So, and you joint optimize the machine learning with the physics model.
Yep.
And as you refine your detailed understanding, you refine that you effectively do numerical solutions to the physics model from first principles by saying, what granularity you do it fine grain in the places where you need more detail, because that's where it's going to trigger the butterfly wing effect or whatever. But you just be coarse grain everywhere else, and that's fine. But you do that because you have this Earth observation data, which has driven a machine learning model, and now they're not so the fundamental model gives you explanatory power, but you can't solve it everywhere, but you can optimize it, solving it at different levels of detail by using the machine learning model, which then is now explained, and you can remove mistakes in it from that as well, which I think is a lot of hope in that approach. And the work I've seen, it's been quite small scale, but it looks really, really, that joint optimization trick is really good when you have two models. And maybe it goes back to this question that Adrian was talking about, where you have a model of societal bias or human bias, and then you look at the model that you've trained an AI on some data from people, and you can look at the two together and see where the issue is. But the issue does require you to have an actual social model that says, oh, wait a second, maybe you've got a blue person bias in your people, and you've just trained the AI to include that. I don't know how do we do that, because society, is society more complex than the atmosphere?
Ooh. Well, society lives in the atmosphere. There's one example which is quite interesting, which is about forest health. So we don't quite know why trees globally are exhibiting higher mortality right now. So with more CO2 in the atmosphere, they should actually live for longer. But it's something to do with the hydrology of their root systems. But Bill Andreg published a paper last year in Nature showing that it's repeated droughts that cause damage disproportionate to some species. And so it's not the first drought, and that's usually the thing you observe. It's the repeated ones that cause a real kind of drop-off in tree health. But that only applies to North American forests. So how do we apply that to tropical rainforests or seasonal dry or temperate rainforests here in Europe? And so that's a good example of what you just described, where you could build a computation model, and then you want to sort of refit it somewhere else based on global. So the explainability process would then be, how do we tweak the physical computation model we've constructed to apply somewhere else. You're looking for this set of differences that you can apply to look for what does it mean to be different between the equatorial belt versus the North American seasonal dry forest. And so I'm hopeful that similar things will apply to societies, but that's way beyond my realm of expertise.
I was going to make another link there, which is we're using about 4% of the world's electricity to run the cloud, which is doing all this computation for us. But I think you could probably justify that for the one model of the planet, which we only have the one planet for. But I think it's hard to justify it for really better targeted advertising or Netflix recommendations. So yeah, maybe we could apply a carbon tax to foundation AI models that don't do something that actually is saving the planet.
It's creating one model of the planet that we all agree on is probably the justifiable one. But I think that convergence is there, right? Because there is an objective truth about how physical systems are evolving, and they can be independently observed. So it feels that's achievable. I'm not sure that agreeing on how society should function is an achievable goal, but it certainly is for the physical processes that we're trying to monitor.
So Adrian, do you want to come back on the models and bias, or on or possibly on Ian Firth's question, which is very cool?
Sure. Maybe I'll start with Ian's, then I'll come back on the next question. I think so. Ian's question is a really good one. I'll try to paraphrase it. I don't know if we can let Ian speak for himself if I'm sort of misinterpreting it. Roughly speaking, I think Ian is saying, well, in the past we had good old-fashioned symbolic AI, and maybe that hasn't achieved as much impact in some sense, but we understand what it's doing, and maybe that's more important. So maybe we should not proceed with these fancy machine learning models that we don't understand, and we should stick with these GoFi models. And I think that's a very understandable reaction. But I want to ask a sort of related question, which is, what does it mean to understand a model at all? So I'll maybe go back to the 70s. I think it was the 70s. I'm sure John will know. The proof of the four-color theorem. So the four-color theorem, probably many people know, is a simple sort of mathematical theorem. It says if you've got a map of the world and you want to color it in so that no two adjacent countries have the same color, it turns out you only need a maximum of 4 colors. You can always color in a map with just 4 colors. You never need 5 colors. And that was a sort of conjecture for about 100 years. Actually, there was a proof that turned out to be a wrong proof that I think got Kemp elected to president of the London Math Society or something in the 19th century. But it turned out people couldn't solve this problem for a long time until something like the 1970s. And the way they solved it, which I'm going to claim is sort of like good old-fashioned symbolic AI, was using symbolic AI techniques to basically reduce this problem to, I can't remember how many it was. I think it's something like 400 or 500 subcases, and exhaustively explored all those cases and showed that in every single one of those cases, the thing worked out. And they were clever to show that if it worked out in all of those subcases, you could always combine them together and the whole thing would work. So I'm going to claim that's a bit like a GoFi approach. They knew what they were doing. But at the end of the day, how do you know if that's right? You end up with this proof that was hundreds and hundreds of pages long. Subsequently, I think some clever people have made it only 200 pages long, something like that, by reducing the number of cases only to 100 or something like that. But still, it raises really interesting philosophical but also kind of practical questions. What does it mean to really understand something? So if you knew that you had this whole big thing that you could check, and if you had time and energy to check it super carefully, and you knew you wouldn't make a mistake, in principle you could check this thing and kind of understand it. But it's pretty hopeless for most of us to think we can hold all of that in our head. So is that understandable or is that not understandable? And similarly, actually, another view of our neural networks is they're really symbolic at the end of the day. They're just pieces of computer code. And you can look at that computer code and you can understand exactly what every instruction says. It is sort of symbolic in that sense. So I don't think the distinction is quite as clear as we might like. And I'd also suggest that, well, I suggest that one way to make progress is to think about a specific context, specific setting where you believe understanding is important, and think, what exactly is it that you want and why? What kind of information specifically is important to provide to whom for what purpose? And can we have some way of measuring that? So as an example, medical diagnosis systems are starting to be automated, and there's great hope for that because you might be able to provide close to human levels of expertise at scale to lots of people at low cost, and that's really exciting. But often it goes wrong, and people quite rightly say, well, we need to understand what these systems are doing. Okay, well, what exactly do we mean by that? And I'd suggest that it's something like we want to provide some additional information to a clinician which enables them to improve patient outcomes. And you can measure patient outcomes over time. And the question of whether it's a good explanation or not can be quantified by, well, how much has it improved patient outcomes? So I kind of like that formulation because it's very easy to get a bit confused or sort of romanticized, seduced by this idea that we want an explanation. One point I think is really important to take away, that I don't think it's nowhere as simple as a binary thing that you either have an explanation or you don't have an explanation. The question is, what information exactly do you want, and how is that going to be useful, and how are you going to measure it?
Nice. I actually saw a presentation by Georges Gontier of the Microsoft proof of the 4-color map problem, where they proved the program that proved the 4-color map theorem, and it's only 12 pages long. But then somebody at the Académie des Sciences in Paris, where this presentation happened, a very ancient French philosopher, mathematician, stood up, very long grey beard, and he said, but how do you know your proof computer is correct? And they just turned around and said, how do you know your brain is correct, sir? And you know, that's the crux of the philosophical problem is actually, does it matter if you're pragmatic and you actually just want the outcome repeatedly, and you haven't come across a map where
Yeah, but can I come back on that, because I think that raises lots of issues, but two I want to make. So one is this analogy with human brains. How do you know your human brain is correct? And on the one hand, I kind of agree with that, and then I'm going to make a point in a minute or two that doesn't agree with that. But kind of going with that, to some extent, we're comfortable with the idea that we humans are not always correct, but we kind of know that often we're correct, and we have some sense of when we're likely to be right, when we're not likely to be right, and we go with it because it works, even if we're not 100% guaranteed that it'll always work. We do that with some other systems. We do that with airplanes. We do that with drugs. Even if each of us is not really sure exactly how they work, maybe no one really is sure how they work, still we go with them because they seem empirically to work reliably well. Now, some people say we should do the same thing with AI systems, and maybe that's true, but I also want to raise a point in the opposite direction, which is one reason, well, we should distinguish between being comfortable with humans sometimes making mistakes and the situation with AI. With humans, we've obviously evolved with each other for millennia, and we've evolved good ways. We've got evolved good senses to sort of get a good idea of when things might go catastrophically wrong, when they won't. If we see someone perform at a certain level, we have a good sense of how likely they're to perform doing similar things. We're not perfect, but at least we sort of stabilize from an evolutionary perspective. With AI systems, they can perform in very different ways. So that's dangerous because we might see them perform very well at some task, and then on some very similar tasks, which to us seems like it's almost identical, they might go horribly wrong. And that's one reason we need to be particularly careful.
So, you know, on that topic, there's two papers I just pasted into the chat. One was Georges Gontier's original paper on proving the 4-color theorem, and one is another one on specifying the French tax code. And for both of these systems, it took about 30 years to go from the computer intuition to a very precise formal specification using for example, a Koch theorem prover, but exactly what it means. And I think that iterative refinement is really important, right? Because you're going from discovering the possibility of a solution to then going, well, I actually need human intuition to describe precisely what all these unknowns and all these alternatives are. And so in the case of the French tax system, there is a formal specification, not using machine learning or anything, just using normal programming language techniques. But it encodes all the uncertainties, and then they used it to check the real legislation of the French tax system, and they found bugs in it because there was inconsistencies and logical contradictions all over the place, which have been legislated over. So instead of expecting our model to understand and to explain it, you can do an independent re-implementation using quite precise techniques these days and show equivalence between the two. And that might be a slightly more successful way of having sustainable ways, sustainable not in terms of energy use, just in terms of human expenditure, to make sure that these models are actually something that can last into the future. you don't need to depend on a probabilistic model. Just use computer science and formal verification.
Can I just respond to that? Because I think often that is a really good idea. At a high level, we're saying if you've got some really complicated model that's really difficult to understand, try to replicate it with a much simpler model, which you can just understand, and there you go. And that can be really good. It's really good if from the beginning you decide, hey, I'm going to use a simple model which kind of is interpretable by design because it's sufficiently simple that that I can understand it, and you can show that it works well enough that you can use that. So Cynthia Rudin pushes that very hard, and I think she's quite right. If you can use a simple to understand model, why wouldn't you? Completely. On the other hand, you also need to be a bit careful, because if it turns out that in fact you need a complicated model, and then you are telling people that they understand it because they've got a simple model which often performs the same as the complex model, well, be careful, because by construction, you actually really need the complex model. And obviously, sometimes the complex model is going to be different from the simple model. That's why you need the complex model. So assuming that it's behaving like the simple model is, of course, in some cases misleading and could get you in a lot of trouble.
Right. I think that's I think that's the problem with the parallel models. There's parallel models of societal problems by different societal groups which don't involve an AI. And I think the stereotypical thing that I mentioned earlier was the custodial sentences in American courts where an AI is trained on data, but it turned out that when the same case came up but with somebody of African descent, whatever, in America, would have been a much higher chance of a custodial sentence from the AI because it was trained on that data. But the reason people knew was that social scientists had studied the judgments, not that they looked at the AI model, but that it wasn't lawyers and judges looking at the judgments who had already obviously made the judgments. It was some people from a different expertise and a different background who came to the problem with a wide knowledge of societal problems. That was sort of their business, if you like, was understanding things going wrong in society. And it could be, you could imagine just saying that we need many sources of diversity in training people and training programs. And that goes back to this climate systems, I think, which is very powerful, that we know that these aggregations of multiple models of climate turn out to be more precise than any single one of the subsystems, which was a surprise to a lot of people. And it wasn't that that they were just masking over errors or papering over cracks. It was something more deep going on, which is quite interesting. I'm conscious of time, and I know people have a kind of hard deadline in 8.5 minutes. So let me give a last word to each of you. Anil, would you like to say some more of your inspirational and positive thinking about the world of sustainability and what we're doing? Or
it's really early days for planetary computing at the moment. We have more agency to take the data available to us and find real interventions to help fix some of these global crises I mentioned earlier. And I think in particular, what Adrian said about people with a wide range of skills, that is beyond just computer science. So we're working with economists, social scientists, historians, ethicists, philosophers, all to figure out what kind of world do we actually want to build that is sustainable in the next 40 years. What does that look like when you close your eyes? And I feel that once we can construct that steady state kind of a balanced consumption world where emissions are counterbalanced with a natural world, then I'd be happy that we've left the world a better place than we entered it. And there is the possibility of trying to figure out exactly how to craft that in the time we have available in the next decade or two, using AI and planetary scale computing. So I'd love to hear from anyone who is interested in this space, this emerging space, and collaborate and working that together and getting the good ideas everyone has as well.
And we're all contactable via university email, so please do. Adrian, last word from you.
Fantastic. So first, I completely echo Anil and your John statement there. We need lots of different voices to be involved. So yeah, please do contact us. I'm sorry that we haven't had a chance to get to all these great questions, but I'm going to briefly comment on the question we had before about tweaking the model and societal biases. I would say one really difficult issue is for any given context, what exactly do we mean by fairness and bias? And one reason that's challenging is that reasonable people might disagree. So whatever decision you make is likely to benefit some people and hurt some other people. So people may have quite different perspectives. But let's suppose that we could hypothetically figure out what we mean, and we could encode that in some simple rule. And I fully recognize that will not always be the case, but you should know that in the technical machine learning fairness world, most people generally make that assumption. They say, well, maybe you mean this. And they come up with some mathematical constraint that can be made very precise. You can state it precisely. For example, you might say, if we're going to make bank loans to people, we need to make equal shares to men and women. I'm not saying that's the right thing to do, but you could imagine some people might think that's the right thing to do. And papers are written where people say, if that's what you think, then you can test your model to see the extent to which that's true. And if it's not true, you can introduce that constraint and retrain your model so that that will be true. And you can think about it as there's a sort of decision boundary that the model has about certain people will get loans and certain people won't. And what the model is going to do with that constraint is going to shift the decision boundary until it is true. Now, there's a follow-on question about, well, how exactly is it shifting that boundary and who's benefiting and who's it hurting? But we'll leave that for another day. Thank you.
Okay, right. Well, I'm really sorry to people who haven't managed to answer your questions, because there's some really great stuff there. But we could go on. And I think this is quite an exciting space. I think we're right to be mostly optimistic about these two problems, but I've just read another terrifying book, a science fiction book, fictional, but about the climate, which just got me worried again. And then I hear Anil talking, and I get slightly less worried. So, Anil's also posted the links to in the chat, and the Gontier paper and the recent Hinton paper, which was I read that, and it's interesting, and those kinds of steps are kind of hopeful. The human brain, a question about the human brain and being biological AI being efficient, it's quite energy efficient, but it's not that good, but it does things completely differently. Artificial neural nets have very low degree connectivity compared with the human brain, as far as I know. And the kind of structure of the brain is quite different, but also at a sort of phenomenological level, if you just show a 3-year-old child a cat the first time it sees a cat, and they're learning the word "that's a cat," and then you show them the pink panther and they'll say "that's a cat." That's an incredible thing. It's one example, but it's actually, the brain, of course, has applied many models. It said, you've got a creature with 4 legs and furry, and it's got a tail that seems to be articulated and pointy ears and whiskers, and incorporated all those features into this model from a whole bunch of weird kludges that have evolutionary. And that's not how most neural nets work, I don't think, but they could. But you probably then have to embody the neural net in something that also has a subjective understanding. So when it sees a cat moving and it sees its own, you see your own arms moving, that's the same kind of thing as I'm used to seeing since I was born, or even before you're born, you might have some notion of movement. So I think there are many reasons why it's artificial neural nets are just not comparable, going right the way from the highest level of models all the way down to the actual wetware, if you like, but we could go on about that as well, but we're actually out of time. Thanks again for all those questions, and thanks very much to Anil and Adrian for finding the time to talk to us in this exciting topic.
Great fun. Learn a lot every time.
Thanks so much, John. Thanks, Anil.